Welcome to section 3.5, and what we are dealing with in this section is the derivatives of the trigonometric functions. And so we do have some new things to learn, but and just like in trig, if you know the three main ones, the sine, the cosine, and the tangent, you can figure out all the others. But there are instances where if you know the others, the three cofunctions, then it's a little bit easier to remember. So as part of notes, we're just going to be taking derivatives. The derivative of sine is cosine. The derivative of cosine is negative sine of x. The derivative of tangent of x is equal to secant squared of x. The derivative of cotangent of x is negative cosecant squared of x. Then the last two, the derivative of the secant of x is equal to the secant of x tangent of x. And finally, the derivative of cosecant of x is equal to negative cosecant of x cotangent of x. And if you notice, there's something very familiar. The regular functions are all positive, the cofunctions are negative, and they are somewhat opposites of each other. If you know tangent, secant squared, cotangent becomes the cosecant squared. Secant is secant tangent, and cosecant is cosecant cotangent. And these are related in the same way that many of the identities are as well. So here we are ready for a particular example. Example number 1. We are asked to find the derivative. Y equals the cosecant of x plus cotangent of x times the cosecant of x minus cotangent of x. Now here is chain rule, or not chain rule, the product rule being asked for over and over again. So we're going to leave this one alone. Cosecant of x plus cotangent of x times the derivative of this. Well, the derivative of cosecant is negative cosecant x cotangent x, and the derivative of cotangent x is a negative cosecant squared, so that will become plus cosecant squared of x. Plus, now we have to take the derivative of this and leave this one alone, so I'll just write the one that is left, and then the derivative of cosecant x is negative cosecant x cotangent x plus the derivative of cotangent is a negative cosecant squared, so I'm going to have to come in here and this becomes a negative cosecant squared of x. And now it's just a matter of putting these all, combining them all together. So FOILing this out, we get negative cosecant squared x cotangent x plus cosecant squared x cotangent x minus cosecant x cotangent squared of x, and the last terms gives cotangent x cosecant squared x plus, now FOILing all this out, we will get negative cosecant squared x cotangent x for the first terms. The outer terms becomes negative cosecant cubed x. The inner term becomes plus cosecant x cotangent squared x, and the last term becomes a positive cosecant squared x cotangent x. And I've missed the outer term here, or the outer terms here should be cosecant cubed x. What did I do? Here's the first terms. Here is the, no, that should be the outer terms. So what should have happened here is this should have been cosecant cubed x. Okay, now notice what happens. Cosecant cubed x minus cosecant cubed x. Negative cosecant squared cotangent x and a positive cosecant squared cotangent x cancel each other out. Negative cosecant x cotangent squared x plus cosecant x cotangent squared x cancel each other out. And negative cosecant squared x cotangent x plus cosecant squared x cotangent x cancel each other out. So absolutely everything cancels out to become a big 0. So the derivative of that whole mess is a big 0. Realize we could have done a couple of other things. We could have put cosecant and cotangent in terms of sines and cosines, and we would have realized that that all equals 1, so then taking the derivative of 1 ends up being 0. Either way, it's probably about the same amount of work both ways. Okay. So now, let's go on to example number 2. Example number 2 is s equals t to the 4th minus cosecant t plus 18. And all we need to do is find the derivative. There's no product rule required here. All we do is take the derivative of this, bring the exponent out front, that's 4t cubed, and the derivative of cosecant t is a negative, so negative minus a negative will become plus cosecant t cotangent t, and taking the derivative of 18, we get that. And so here is the final derivative, 4t cubed plus cosecant t cotangent t. Example number 3. We are given y equals negative 4 cosine of x, and we are asked what's y double prime. Well, in order to find y double prime, the first thing we have to do is find y prime. Y prime, okay, the derivative of negative 4 cosine x. Well, the derivative of cosine x is negative sine x. And multiply that by the negative 4 that was already here, and we get a positive 4 sine x. So that's what y prime is. Y double prime says take the derivative of this. Well, derivative of sine x is cosine x multiplied by the 4 that was already there, and we get 4 cosine of x. The second derivative of negative 4 cosine x is 4 cosine x. Example number 4. Okay, we are looking for the limit as x approaches pi over 2 of 3 the cosine of the sine of x plus pi times the cotangent of pi over 4 cosecant of x plus 1. It's the plus. Okay, Now, the first thing I'm going to do is see, can I just immediately plug it in? And I think there's no place where pi over 2 causes any problems. So let's just plug that in. So what this is going to become is 3 cosine of the sine of pi over 2 plus pi times the cotangent of pi over 4 times the cosecant of pi over 2 plus 1. So working things on the inside, we have 3 cosine of, okay, the sine of pi over 2 is, oh, wait a minute, this should be negative. So I need to go and change all these. The sine of negative pi over 2, the cosecant of negative pi over 2. The sine of negative pi over 2 is negative 1. We need to remember that from trig last year. Plus pi times the cotangent of pi over 4. Okay, cosecant of negative pi over 2. Cosecant of negative pi over 2. Okay, that's cosecant is 1 over sine, and we've already said that sine is negative 1, so 1 over negative 1 is negative 1, so this becomes pi over negative 4 plus 1. Okay, going on. Next step. 3 cosine of negative 1 plus pi times whatever cotangent of negative pi over 4 is. Okay, well I think here, negative pi over 4, tangent, well cotangent is the reciprocal of tangent. The tangent of negative pi over 4 is negative 1. So the reciprocal would be negative 1. So this becomes times negative 1 plus 1. So this becomes 3 cosine of, okay, I noticed the negative 1 and the positive 1 cancel out each other out, so it's 3 cosine of negative pi. And negative pi and pi are basically the same thing, at least in the cyclical thinking through it. And the cosine of negative pi, or the cosine of pi, is negative 1. So this becomes 3 times negative 1, which equals negative 3. And there, after all that work, we end up with the simple number negative 3. Example number 5. Example number 5, we have this line, y equals 2 minus sine of x, and we are asked to find the tangent when x is equal to pi. Okay, first of all, we need to remember tangent means the derivative. So the first thing we have to do is to find the derivative. Y prime will equal, okay, the derivative of 2 is 0, and negative sine x. Well, the derivative of sine is cosine x, so this will be negative cosine x. Now, we need to figure out what will the slope be, because this tells us the slope. So we're going to take y prime and put in pi. That's negative cosine of pi, which equals negative 1, or positive 1. So the slope becomes 1. Now, if we're asked what is the tangent, we're asking what is the tangent line. So we know the slope. We also can fairly easily find what will the point be. Now, to find the point, we know it's going to be pi for the x value, and then to find the y value, we have to plug it in here. 2 minus the sine of pi. Well, the sine of pi is 0, so 2 minus 0 is 2. And so, we know the slope is 1, we have the point pi, so we can say y minus 2, the y value, equals the slope times x minus the x value. Y minus 2 equals x minus pi, and add 2 to both sides, so that the final answer is y equals x minus pi plus 2. This is the tangent line to 2 minus sine x when x is equal to pi. Example number 6. Example number 6, we need to find all points on the curve y equals sine of x. Between, when x is between 0 and 2 pi, so we only have to go one revolution, where the tangent line is parallel to y equals 1/2 x. Now there's several things that we need to look at. First of all, being parallel to this line, we know parallel lines have the same slope. So the slope we're looking at is that right there. The slope we need is 1/2. Now how do we find the slope of this? What we do is we take the derivative, just like always. So to find the slope, the derivative of sine of x is the cosine of x. So we need to know, where does the cosine of x equal 1/2 in just one revolution? So cosine of x is equal to a positive 1/2 in either quadrant 1 and quadrant 4. We need to remember that all students take calculus stuff, you know, and cosine equals 1/2 is going to be somewhere here and somewhere here. And so we need to come up with what's that angle there and what is this angle right here, because it has to be between 0 and 2 pi. So where cosine is equal to 1/2 would be pi over 3. That's this first angle right here. And then going all the way around, that would be 5 pi over 3. And so we have the values pi over 3 and 5 pi over 3 are the places where this will occur. Let me make sure that that's correct. Cosine of x equals 1/2. Yeah, that's a pi over 3 and 5 pi over 3. So now we need to find the actual points. So we're going to plug in pi over 3 into the original. So at pi over 3, the sine of pi over 3 is root 3 over 2. And at 5 pi over 3, we figured out, okay, the sine of 5 pi over 3, we know the sine is negative, but it's going to have the same reference angle, so it'll be negative root 3 over 2. And so the final answers are pi over 3, root 3 over 2, and 5 pi over 3, negative root 3 over 2. Example 7. Example 7, we are given the position. This is what we did a whole bunch with last week. This time we're just throwing in some trigonometric functions. We need to find the body's acceleration when t is equal to pi over 3. Well, to find acceleration, if this is position, acceleration, or the first derivative, is velocity. And the second derivative would be acceleration. So, the velocity, this becomes 0, and the derivative of pi cosine t is negative 5 sine t. And then the second derivative of this, the derivative of sine t, is cosine t, so it becomes negative 5 cosine t. So I need to figure out what is s double prime, and we are asked to find when it's pi over 3 seconds. So we get negative 5 times the cosine of pi over 3. Well, very quickly, I need negative 5, and then the cosine of pi over 3 is 1/2. Cosine of pi over 3 is 1/2, so that would be negative 5/2. Negative 5/2 what? We are told meters in seconds, so negative 5/2 meters per second squared, because we are dealing with acceleration. Example number 8. Example number 8 has this function, s equals 9 sine t minus cosine t. And find the body's jerk when t is equal to pi over 4. Okay, so velocity is s prime, acceleration is s double prime, and jerk is s triple prime. So we're going to have to find all three of these. Okay, the derivative of 9 sine t is 9 cosine t. Derivative of cosine t is a negative sine t, so this becomes plus sine t. Now we have to take the derivative of this. Derivative of 9 cosine t is negative 9 sine t, and the derivative of sine t is cosine t. Now the third derivative. Take the derivative of this. The derivative of negative 9 sine t is negative 9 cosine t, and the derivative of cosine t is a negative sine t. So I'm going to have to change that to a negative. And now we can finally plug in into s triple prime pi over 4. So we get negative 9 times the cosine of pi over 4 minus the sine of pi over 4. Well, the nice thing about cosine of pi over 4, that is root 2 over 2. And sine of pi over 4 is also root 2 over 2. So we end up with negative 9 root 2 over 2 minus root 2 over 2 is negative 10 root 2 over 2, or more simply written as negative 5 root 2. Now, the jerk will be in meters per second cubed. Technically, it's not meters per second cubed, it's meters per second per second per second. But that's an easier way to write that exact same thing. Okay, we have a couple more examples, but notice nothing, well, the thing that's new is the trigonometric functions here, and it's just a matter of learning those 6 rules. Okay, now the question becomes, we are asked to find what is the 998th derivative of x of the sine of x. Now here we just need to do a little bit of thinking. What's the derivative of the sine of x, the first derivative? That becomes cosine of x. The second derivative of sine becomes negative sine of x. The third derivative of sine is negative cosine of x. And the fourth derivative of sine is sine of x. And notice what it starts to repeat, because now we'll take the fifth derivative, which is just the derivative of sine, so every 4 it's going to repeat. So the question is, where are we at in that cycle? You know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so on and so forth. Obviously, we don't want to count to 998, but understand that this would be the 996th derivative. That's a multiple of 4. So this would be the 997th, the 998th. So the 998th derivative of sine of x is negative sine of x. This is very similar to I and I squared and I cubed and I to the 4th power. It's the same cyclic pattern. And number 10. It says graph y equals negative tangent of x. Okay, we need to do some remembering of what a tangent line looks like. We have to remember that at negative pi over 2 and pi over 2 there are asymptotes. So I'm going to put those in. And we are asked to do it between negative pi over 2 and pi over 2. And there happens to be asymptotes right at that point. Now, tangent of x would normally start down here on the left and then go up and hit the origin and then go up like that. looks sort of like a cube function, but it's really a tangent. So y equals negative tangent of x is going to be reflected over the x-axis. So we're going to get something that looks like this. It's going to come along here. It's still going to go through 0, and then it's going to fall down like that. So this is more or less what y equals the negative tangent of x is. But we also need to find the derivative. Now remember, if we have the graph, the derivative is simply the slope. So what slope is right here? Well, that's a very much negative number, so it's going to be way down here. Here it's beginning to be about maybe -1. And here it's getting close to 0, but it never quite reaches 0 because it's still going downhill. So it's getting closer and closer to 0. Then about here it goes back down to -1. And then about here it's really deep again. So the derivative here is going to look something like this. Or something very similar. And so we have done what they've asked, except it says, is the slope of the graph of y equals negative tangent ever positive? Well, it was never positive here. It was always negative. So the question is it ever positive? Well, we have to remember that tangent is cyclic. So that means over here it's going to look exactly the same. Over here it's going to look exactly the same. And so it's just going to keep on doing that over and over again. And each little part, the derivative will always be negative. So it says, will it ever be positive? That answer is no, it will never be positive. Explain. Well, tangent of x is cyclic. In other words, it's just this part right here repeated infinitely many times. And if this one cycle never had a positive derivative, then then it will never have a positive derivative because it just repeats and repeats.